increases the pressure of the velocity of the fluid at the expense of pressure, while a diffuser is one that increases the pressure by slowing the fluid down. So let's look at both. So you can see that the velocity at the outlet is higher than the velocity at the inlet for nozzles at the expense of pressure. While for diffusers, the velocity at the outlet is lower than the velocity at the inlet for increased pressure. Now, if we want to do the energy balance of these two systems, we could write it like this. First of all, we assume that Q across the boundary is 0. That is, no sufficient time for any significant heat transfer to take place. Hence, we say Q is 0. Then we also say the work done is also 0. The potential energy, PE, is very negligible, so we can also safely assume that it is 0. However, the kinetic energy is not small, because the kinetic energy is the result of the change of velocities of the two sides of the nozzle. So, kinetic energy remains for the nozzle. And also, for diffusers, we could say similarly. We have the work done is 0, the heat transfer is 0. Like earlier said, no sufficient time for any significant heat transfer to take place. The potential energy is also 0, but the kinetic energy has changed from very high at V1 to very low at V2. Okay. Let's take an example on nozzles at 10 degrees C. Air at 10 degrees C and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 meters squared. The air leaves the diffuser with a velocity that is very small compared the inlet velocity compared with the inlet velocity. Determine A, the mass flow rate of the air, and B, the temperature of the air leaving the diffuser. As usual, let's begin with stating our given values, and then we'll step up to trying to obtain a solution to the question. So the fluid is air. We were told that P is 80 kilopascal at entrance, that the T at entrance is 10. Now let me point out something here. When you refer to temperature, you can use one of the two. Either you use small t or big T. But these two things cannot be used interchangeably. You use small t for degree C and big T for Kelvin. So now in this question, we're giving our degrees, our temperature in degree C. So that's why we're using the small t. We're told the inlet velocity is 200 millimeters per second, and the area is 0.4 meters squared. We want to find the mass flow rate of air through the diffuser and also the temperature at the exit of the diffuser, T2. So first, let's begin by trying to determine the mass flow rate of the air. Remember, recall that m dot is equal to rho AV, which represents the velocity. So the density of air was not given to us, but we can calculate it. Recall that PV is equal to RT. So I can get the specific volume. I should actually put MRT so that P times V, capital V over N is equal to RT. And then P times small v is equal to RT. I've made this now the specific volume over mass. So now I can also write that small v is equal to RT over P. Now R is the gas constant for air, which is nothing but 0.287 times the temperature T1 and P1 and pressure P and divided by the pressure P1. Now remember our temperature is in degree C, but this formula takes temperature in Kelvin. Therefore, I must convert from degree C to Kelvin. So to do that, I'm going to add 273.15 plus 10. Everything divided by the pressure, which is 80 kilopascal, which returns to me the value of 1.015 meter cube per kilogram. Now I have gotten the specific volume, V1. We recall our equation that m dot can also be written as the velocity V times the area A over the specific volume. We derived this equation earlier. So if I put everything into here, I would have the velocity of 200 meters per second times the area of 0.4 divided by the specific volume of 115. And this will give me 78.8 kilograms per second. Furthermore, to get the temperature at the exit, we have to do the energy balance of this. So to carry out the energy balance, I'm going to write a very simple formula, which is going to be that E energy in is equal to energy out. If that is true, I can also write that m dot from our equation. Remember we have so E in is equal to E out. Now, if you recall our balance equation, you recall that we had something of the form U1 plus C1 squared over 2 plus Z1 G plus P1 V1 is equal to U2 plus C2 squared over 2 plus Z2 G plus P2 V2 plus W plus Q. Okay. So recall also that the following terms are tending to 0. First of all is this potential energy term. It goes to 0. Next, this term also here goes to 0. These two terms can be brought together. These two terms can be brought together because H is equal to U plus PV. So because H is equal to U plus PV, then we can write that H1 plus C1 squared over 2. In this case, let's reconstruct our nomenclature. I'll use V. This whole energy flow times M dot is equal to M dot into H2 plus V2 squared over 2. Now, this will mean that H2, if I make H2 subject of the formula, I will have is equal to H1 minus bracket open V2 squared minus V1 squared all over 2. Now, this equation has H as a variable, and we're interested in the energy at state 2. So because of that, we need to determine what is the energy at state 1. How do we know that? We go to air tables. We'll say for air, H1, but H1 is equal to, from air table, is equal to 283.14 at 283 Kelvin. Okay? Because if you recall that H1 is equal to CPT, and CP of air is equal to 1.005 times the temperature at that point, which is 283. Hence, I can therefore plug this into the equation. H2 is equal to 283.14 minus V2 squared, which is, of course, remember we were told in the question that V2 is 0. So 0 minus 200 squared divided by 2. Everything, of course, times 1000. Why am I doing that? It's because this unit is in kilojoules per kilogram. So I have to also convert whatever I get here to kilojoules per kilogram. Hence, we are going to then have that H2 is equal to 303.14. If this is H2, therefore T2, which is equal to, I'm going to make T the subject of the formula. Okay, let's take it step by step. H2 is equal to CPT2, which implies T2 is equal to H2 over CP. And therefore T2 is equal to 303 Kelvin. Now, small t2 is equal to 303 minus 273, and that is 30 degrees. Okay. Now we move on to other engineering open systems. And we want to see how to apply the energy equation for those kind of systems. For compressors and turbines, fans, pumps, throttling valve, mixing chambers, heat exchangers, pipes, and ducts. So we want to look at these systems and how to apply the energy flow equation on them. Okay, so these are several machines we see in engineering, and we can write how to analyze the several equations we have for these particular machines. So taking the compressor as an for the first one, we have that the potential energy is zero, obviously because of the very small value it has. Then the kinetic energy is also zero because the velocity is too low. Then we know that the work is a negative work because it's a work input. Then we also know that the heat through it is zero. Sometimes we even have, unless we have what we call intentional cooling, okay? So for compressors, sometimes it's done. Then we look at, for turbines, we have Q is equal to 0, P dot E is equal to 0, that's the potential energy, okay? The heat through the turbine is 0. The kinetic energy is also 0 because velocity is high, but although the velocity is high, which gives kinetic energy, although the velocity is high, the value is very small compared to the positive work that is gotten from the turbine. So work, it has a value and it's positive. Then also for fans, we have a negative work, which is a work input, while a turbine is work output, pump also a work input. And we have also potential energy to be 0 for fans, the kinetic energy to be 0 for fans. Okay. And we know the aim of fan is to mobilize the gas. Now we have the pump. For the pump, we have the potential energy as 0, the kinetic energy as 0, and the work to be negative, and a work input, work output. Then for throttling valves, it's a very simple one. The enthalpy at state 1 is equal to enthalpy at state 2. That is, U1 plus P1 V1 is equal to U2 plus P2 V2. For mixing chambers, we first of all, when it's fully insulated, therefore the Q, the heat flux, is 0. The work done is also 0. When we say there's no work in the mixing chamber, the kinetic energy Ke is 0. The potential energy is also 0. And an energy balance of the mixing chamber says the mass in is equal to the mass flow rate out, and the energy in is equal to the energy out. For heat exchangers, we first of all say that it's fully insulated, on the outer wall, therefore the Q is 0. The work done is also 0 across the boundaries. The delta KE, the change in kinetic energy, is equal to the change in potential energy, which is equal to 0. And then sometimes we also say, most times we say the Q, that's the heat of fluid in one part of the heat exchanger, let's say fluid A, is equal to the heat gained by the other. Heat lost by fluid A is equal to heat gained by fluid B. For pipes and ducts, we cannot at this point say anything about this because the pipe could be insulated, it could not be insulated, so we just say it depends on condition. Okay, so with this we have covered all the systems found in engineering, most of the systems. Now these things give you an idea on how to apply our open the equation for open systems, that is for steady flow systems. So when you have these equations, you know which part of the equations remain and which part to analyze and which part goes to 0. Now we'll take another question using the steam as a fluid. So let's go. Consider a steam turbine that produces 5 megawatts and it's adiabatic. Take the inlet that is produces 5 megawatts adiabatic. Take the W out. The conditions of the turbine. P1 entrance to the turbine is 2 megapascal. T1 is 400 degrees C. V1 is 50 meters per second. Z1 is 10 meters. Point 1. State 2. First of all, it's adiabatic, meaning no heat flow, no heat crosses its boundary. The pressure at the outlet is 15 kilopascal. The dryness fraction of the steam at outlet is 90%. The velocity at outlet is 180 meters per second. And Z2, that's the height at the outlet, is 6 meters. Now, the first thing we're going to do is to calculate. We have the pressure and the temperature, 2 points. 2 properties fixing a state point. So that means we can also find the enthalpy at state 1. So for this thing, H1 is equal to H at 2 megapascal and 400 degrees C. From the tables, you can read that H, that's from steam tables. An example of a steam table is that prepared by Rogers and Mayhew. So we can use that to get our value. So we'll have 3248.4 kilojoules per kilogram. Then also we can also get the H as state 2. How can we find that? We have the pressure at state 2 and we have the dryness fraction at state 2. So to do that, I would say, given the dryness fraction, that means to us that this steam is what we call the wet steam. So because it's the wet steam, the formula for calculating H2 will be H equal to HF plus dryness fraction HFG, all at P2. So this will give me HF at that point is 225.94 plus 0.9, which is the X dryness fraction, times HFG at 15 kilopascal, and that is 2372.3. Solving, I would have 2361.01 kilojoules per kilogram. Okay. Now, the next thing we have to think about is to get, okay, we have H at state 1 and we have H at state 2. So I can then find the difference in enthalpy. So delta H is equal to H1 minus H2, and that's going to give me 3248.4 minus 2361.01, and that gives me minus 887.39. Next is to find the difference in kinetic energy, Ke, and that is going to be the velocity, the difference of squares of velocity. So in this case, I have V2 now let me point this out, that if we start by saying H2, if we say H1 minus H2, we have to use that convention throughout. So for this case now, I'm going to do a change to what we got initially for the enthalpy. I'm going to change it to H2 minus H1 so that we can continue with that convention. So this will be 2361.01 minus 3248.4, so that we can be consistent with signs, because at the end of the day we could be able to know whether what is happening in terms of using the sign that we are getting from the equations. So back to our calculation. In this case now, since I've used 2 minus 1, I'll also use V2 squared minus V1 squared over 2, and that's going to give me 180 squared minus 50 squared over 2, and of course to convert to kilojoules, divide by 1000, and that's going to give me 14.95 kilojoules. I can do the same for potential energy. We have delta PE is equal to G, gravity due to acceleration, Z2 minus Z1. Again, I'm following that same convention, and that's going to give me 9.81 times 6 minus 10, and that is minus, that's a negative value, and that's minus, of course, I'm going to convert to kilojoules as usual, divided by 1000, and that's minus 0.04. So now, these are the different quantities of energy for that system. Now, I want to determine the work done per unit mass. Work done per unit mass of steam. So to get the work done per unit mass, what I'm going to do here is to calculate the work output. Okay, to get the work output. So to do that, now from the energy equation, we have that the work out is equal to, of course, work output. Okay, I'm going to, okay, let's derive this step by step. Okay, we have m dot h1 plus v1 square over 2 plus gz1 is equal to the work out plus m dot h2 plus v2 square over 2 plus gz2. And remember, Q is equal to 0, so Q is not in this equation. Since Q is equal to 0. Therefore, I can put these two together and get work out. Therefore, work out is equal to H1, 1 minus 2, isn't it, right? So because we're going to have state, if I take everything here over the equality sign, I'll have in state point 1s minus point 2s. However, we have already used 2 minus 1. So I will put a negative sign here, okay, and so that I can use the 2's minus 1's. So if I do that, I will have work output is equal to H2 minus bracket open H2 minus H1 plus delta KE plus delta PE. And if I put everything together, I already have, I call this delta H now, okay? So we can therefore write that is negative into delta H minus 887.39. Okay. Then what's the value here? Is a positive plus 14.95. And what's the other value? Is a negative minus 0.04. So if I put everything together, I'm going to get 872.48 kilojoules per kilogram. Now, having that, we are now going to say, how do we get the mass flow that flows through the turbine? I can get that by getting the total work output of the turbine, dividing it by the specific work of the turbine. So if I do that, the mass flow M dot is equal to 5,000, which is 5,000 kilowatts. I'm converting from megawatts to kilowatts. It was 5 megawatts, which I've converted to 5,000 kilowatts, divided by 872.48. Okay, that will give me so that will give me 5.73 kilogram per second. Recall again that this is the specific work per unit mass. While this is the total work for all the mass. So if I want to get the value of the mass, I will divide the total work for all the mass by the specific work.